In this unit, we will discuss how compact photonic models are created and why they are useful. We will discuss the challenges with photonic circuit simulations, then we'll talk about how to build compact models and use them for circuit simulations. We'll discuss S-parameters as a way of building a compact model for a variety of components. I'll show you how you can create S-parameters for a directional coupler, which can be used for making interferometers or ring resonators. Let's discuss the challenges with modeling photonic circuits. The first is that the optical fields are complex values, namely the electric fields have both amplitude and phase. Not just that, but optical signals have a very large bandwidth. A wavelength of 1.55 microns corresponds to 192 terahertz. As we usually talk about wavelength ranges of several nanometers, or even 100 nanometers, the simulation bandwidth can easily be many terahertz. This makes it difficult for a simulation as compared to electronics time domain simulations because we're going to have a very small step size. Finally, we simultaneously want to know the wideband optical transmission spectrum of a circuit, as well as the time domain behavior for individual channels in data transmission applications. So this requires mixed mode simulation capabilities. To compound the problem, we need to model both electrical signals and optical signals. Unlike electronics, there are no standardized behavioral models. And unlike electronics or mechanical systems, there are no simple equations like voltage equals current times resistance or force equals mass times acceleration. So you can't use common circuit techniques like nodal analysis that are used in SPICE solvers. So each research group or software vendor has been defining their own modeling methodology. Despite these challenges, we need a reliable, compact model library. The libraries need to be built and calibrated for each foundry process, just like in the electronics industry. We can build compact models from either experimental data, from simulations, or a combination of both. This diagram illustrates the physical simulation tools available from Lumerical Solutions that can be used to simulate optical and electro-optic components. The simulation data is used to create models in Lumerical Interconnect for photonic circuit modeling. Here is the first example of a compact model in Lumerical Interconnect. This is the optical waveguide, which is simulated in Lumerical mode. The mode simulation requires information about the waveguide geometry, such as thickness and width. The simulation gives us the effective index, the group index, the dispersion, and possibly data for multiple modes. The data is saved in a format that Interconnect can read. We also need to add some experimental data for the measured propagation loss. This is not included in the simulation since it comes from an unknown amount of sidewall roughness. Let's look at an example of how compact models are used in system simulations to motivate their need. This diagram is a schematic containing a ring modulator and is drawn in Mentor Graphics Pixus. The simulation behind the schematic is implemented in Lumerical Interconnect. Here we see a laser connected to a ring modulator along with some data. The data is received by a detector and measured by an oscilloscope. So what does the model for the ring modulator look like? Let's look inside. We see that there are two directional couplers, waveguides, a phase shifter whose phase is dependent on the voltage, and an electrical low-pass filter to represent the RC time constant of the modulator. The nice thing about this approach is that all these pieces are primitive components that can either be simulated or can consist of experimental data or a combination of both. Finally, we can use these circuit models to simulate the response of the circuit. In this case, we observe the time domain data using an oscilloscope. Let's discuss the directional coupler that is used to make a ring resonator. This is a 4-port device, as illustrated. To make a ring resonator, we need a slight coupling from port 1 to port 4. We can simulate the S-parameters. The graph shows that there is a little bit of light coming from port 1 to port 4 of about a few percent. Most of the light from port 1 ends up in port 3. When you connect two of these couplers together to form a ring, most of the light is stuck inside the ring, hence it can resonate. What's nice about the S-parameters of the directional coupler is that you can simply take two of them, connect them, and obtain the performance of a ring resonator. The graph shows the transmission spectrum of the ring resonator for both the through and the drop ports. We will go through an example of how to simulate such a resonator in a tutorial. Let's discuss what are S parameters. Scattering parameters, or S parameters for short, are used to describe the behavior of a linear time-invariant network. Traditionally, this concept is used to describe the response of electrical devices as a function of frequency. S parameters are particularly useful for experimental characterization of electrical devices using a vector network analyzer, or VNA. They can also be used to describe optical devices with experiments conducted using an optical network analyzer, or ONA. In both cases, measurements are performed over a range of frequencies or wavelengths. The S parameters are complex numbers, meaning they include an amplitude response and a phase response. You can use these S parameters to perform circuit modeling. These simulations will include reflections from components, which is excellent since it includes unwanted effects, such as reflections from grating couplers, Y branches, and so on. And it also includes desired effects, such as reflections needed to make Fabry-Perot cavities, Bragg gratings, and so on. Let's go through how to create S parameters for the directional coupler. Since this is a 4-port device, the S parameters are a 4x4 matrix with one matrix for each wavelength. The rows of the matrix represent the output ports, and the columns represent the input ports. The first step is to inject light into port 1 and measure the light being reflected back into port 1, light scattered into port 2, and light transmitted into ports 3 and 4. The data is placed into the first column of the S parameter matrix. This procedure is then repeated for light injected into port 2, then port 3, and finally port 4. And this creates our complete matrix. In cases like the directional coupler, we can take advantage of symmetry to cut down on the number of simulations. Since this device is symmetrical, you would get the same response whether you inject light into port 1 or port 3. So we only need 2 simulations instead of 4. Another example of a compact model is the fiber grating coupler. This component is well represented by S parameters. These can be measured or simulated using numerical FDTD solutions. The S parameters include both the insertion loss versus wavelength, as well as the back reflections from the coupler.